So good afternoon. My name is Yizhi. I'm a postdoc in AMCR division at LBL. So today I'll try to put a new perspective on observable calculations in metabolic systems. I'll focus on energy calculations, so the slide is titled as spectral estimation. Okay, so the quantum computers are promising for studying many-body systems. And this figure shows a prototypical example that alludes to potential quantum algorithms in solving chemical challenges. Specifically, what I show here is a nitrogen fixation process that converts the nitrogen and hydrogen into ammonia. And then this process occurs with a catalyst called FMOCO, which makes the reaction proceed very efficiently. And understanding reaction mechanism requires knowing actually the energy configuration of the catalyst itself, and therefore solving a complicated Schrodinger equation, even though the reactants or products are pretty simple. And the goal here is really to get the eigenpairs of this molecular Hamiltonian corresponding to the lowest energy. And quantum computers provide a platform to simulate these type of many-body systems. And this is very important for finding stable molecular structures and also transition states in chemical reactions. In fact, up to this day, people are still improving algorithms to study this very specific reaction pathway with the hope of trying to scale up the process to find some industrial application. And our goal is really to design algorithms that are both efficient and compatible with current hardware. So for energy calculations here, I list 3 classes of algorithms. On the left, we have the quantum-based estimation, which is just mentioned by Yulong. So this algorithm outputs the energy in a set of ancillary qubits. So this textbook quantum-based estimation is theoretically attractive because it has optimal Heisenberg limit scaling. But on the other hand, it needs a relatively large number of ancillary qubits to control operations. And also it might require error-corrected computation, which is not quite available yet. Moving down the ladder, we have the adiabatic state preparation, which transform a wave function by gradually changing the Drabant Hamiltonian. So these algorithms already run on existing hardware, but the term adiabatic here suggests that the change in the Hamiltonian can be very slow, which can lead to a larger circuit map. So here we'll focus on the variational quantum eigensolver and its variants, which utilize both quantum and classical resources in an iterative manner. The figure here shows the basic idea of BQE, which is introduced in this morning's talk. A quantum computer is used to evaluate the energy through a parameterized circuit, and then we input these quantum measurements into a classical computer to update the parameters. And even though these BQE-based algorithms, they're near-term friendly, they do not always give accurate energy estimations. For example, the optimization of the parameter space can be very problematic because we know the landscape can be highly non-convex. So in this talk, we will focus on real-time evolution or Hamiltonian simulation as our main workhorse. So we're doing e to the minus ht on some simple to prepare energy state, which we call phi non here. To see the connection between the time evolution and spectral estimation, we can really express the time evolved state in the eigenenergy basis, which is nothing but a sum of sinusoids. So really the energies and their weights are encoded in these composing phases and amplitudes. And why we care about real-time evolution, I think the answer should be pretty clear to all of us. Because one, it's quantumly native due to its unitarity, and second, it's quantumly efficient due to its BQP completeness. So the middle 2 figures highlight 2 recent work that sort of demonstrate the utility of time evolution on both digital and analog devices. And I also want to add that for a digital Hamiltonian simulation, there's a whole zoo of algorithms we can use, many of which already have pretty much near optimal scaling. And our goal is really to learn the spectral information from the dynamics with minimal resource overhead. And in this particular talk, we care about recover the low-lying energies, which are red, essentially barcodes in the spectrum of the many ones. So before I dive into our framework, I first want to introduce or set up the stage for 2 popular classes of real-time methods that sort of form the basis of our work. So these two methods are the subspace methods and the signal processing method. So the idea of subspace method, they really rely on projecting the exact Schrodinger equation onto some subspace of lower dimension. So in exchange, we get a reduced eigenvalue problem that sort of variational approximates the original high dimension problem, shown down below. But because these projected eigenvalues, they're much smaller in size, they can be solved efficiently on a classical. In particular, we care about building a real-time subspace, which is shown on the right here. We would do it and we time evolve a many-body wave function. And as we evolve the wave function, we know the individual eigenfaces, they would wrap around the unit circle at different rates. So our hope really is to combine different time evolved states in the subspace, hoping that the high energy contribution will really cancel out by a phase cancellation. And alternatively, there's this class of method, which I call the signal processing methods. So here I just want to clarify. Okay, so here I want to clarify that by signal processing, this is different from what Yulong talk was about. So here the signal processing is purely done on the classical side using classical signal processing techniques. So here the Fourier-based techniques can really help resolve the target eigenfrequency components. For example, a window Fourier transform, which is shown here, can be used really to isolate out the dominant eigenphases in the time signal. Where F here is a window function in the time domain, and F tilde here is the Fourier transform in the energy domain. So if the F and F tilde, they're both sufficiently decaying, or meaning that their decay is rapid enough, then the location of the spectral peak can be identified pretty efficiently by classical processing. So the subspace method and then signal processing method, they sort of really differ in their strategies. And that's why I want to put out a table that highlights some of the important features of the two approaches. So in the second column, we have the measurement cost for sampling a single data point from the time series. And then both methods, where epsilon1 here is really the statistical error or noise. So the two methods have identical costs because these two methods both typically use a Hadamard test to measure the overlap. And the third column shows the total Hamiltonian simulation cost, where now this parameter epsilon here is the energy estimation error. So for the subspace method, they often don't have an optimal scaling, and moreover are often limited by the short noise or statistical noise. They can also be somehow susceptible to these measurement noise because they're essentially solving an ill-conditioned eigenvalue. And by contrast, many signal processing methods, they have optimal runtime. But if we look at the last two columns, it shows that on the other hand, the subspace method, they do not require the existence of some dominating eigenmodes. So this can, in some cases, make the initial state preparation process very convenient. Also, because the subspace method is solving an eigenvalue problem, it does give us direct access to the eigenstate, which is clearly missing in these Fourier-based techniques. So our question is whether we can combine the relative strength of these two approaches to target ground and excited state properties of a many-body Hamiltonian. And our idea is very simple. So instead of working or processing a single time signal like the overlap, we want to work with many signals that form a subspace. So we do so by sampling many expectation values, or which we call observables here. So they take the form of something like a generalized overlap, where we have compute phi O e to the IHT phi for a set of operators O here. And we'll show that this is achievable with a technique called classical shadows, which is also introduced this morning. And then the great thing about classical shadow is it has a sample complexity that is only logarithmic in the number of operators. And moreover, we'll show that the sample complexity can be made independent of the system size or the locality of these operators O here, which really gives us the freedom to sort of simultaneously estimate a large number of signals at the same time. So we'll call this multi-observable approach the MODM, where DMD really refers to the classical processing part. So I want to go into a bit more detail with what we do with this framework. So first I want to talk about the data collection step on a quantum processor. So here the idea is very similar to an interferometry experiment where we create a superposition state using a single ancilla here. So here phi perp is a garbage state. It can be any state. And we only do time evolution on the initial state we pick, the phi naught. So in some cases, I just want to mention that we can avoid the use of control time evolution acting on phi naught if the phi perp is an eigenstate of the Hamiltonian. For instance, in quantum chemistry, we can just pick phi perp to be the vacuum state with no particle occupation. And then we can replace all control time evolution with free time evolution. So far, the setup is still pretty similar to the Hadamard test in the sense that if we just directly apply some operator O and measure the ancilla, then we still expect the sampling cost to be linear in the number of operators we apply. So to really get down to a logarithmic dependence, instead, here what we do is we try to sketch the time evolved state using classical shadow protocols. And there are two key steps in classical shadow tomography. First is try to do random quench time evolution or random quench dynamics by sampling some unitary from a unitary ensemble. And second is we try to do computational basis measurements. The idea is upon each basis measurements, the state rho of t would collapse into a bit string state. So after many repetitive experiments, we should get something like a classical shadow data set, which is composed of a pair where the first item in the pair is the random unitary we use, and the second item in the pair is the bit string state we get. And it is known that to predict I expectation values, we only need log of I classical shadows. And there's this multiplicative factor of gamma I shadow, which means this is known as the shadow norm, which depends on the choice of the unitary ensemble and also the operator gamma to trace over itself. So remember, our goal is to collect a multi-observable signal, which looks like a generalized overlap, but with a bunch of operators all sandwiched in between. So here we can rewrite this target expectation values as the trace of rho of t with respect to an extended operator, which we call gamma here. So the key message is this gamma really is a low rank operator. So this has implication because if we choose suitable random unitary ensemble, for example, if we do a global Clifford twirling, then we can show that the shadow norm is really independent of the system size or the locality of these O's. So this really allows us to reduce the sampling cost to logarithmic in a number of different observables. Okay. So once we have the estimated multi-observable signals, here we can proceed to the classical post-processing step. And the tool we use here is called dynamical mode decomposition. Rather than solving an ill-conditioned eigenvalue problem, here what we do is we try to solve a least square problem, which is in general numerically more stable. And this least square problem is essentially stacking different multi-observable along a time sequence. And the solution to this least square problem would be some propagation matrix A that advances these expectation values in time. So essentially speaking, the A acts as a time evolution operator, but in the space of observables. So diagonalizing this A matrix would give us eigenvalue and eigenstate information about the Hamiltonian. But I just want to mention that why we call this a signal subspace method is because we can actually map this least square problem to equivalent eigenvalue problem. But the eigenvalue problem is really trying to diagonalize a super operator called the Coupon operator, which lives in a space of functions. So what Coupon operator does is it tries to advance measurement function on the states according to the Hamiltonian flow. So that's like a formal way of put it. But this really, we can really show that this least square procedure reduces to a subspace method applied to the Coupon operator, therefore making a connection between signal processing and the subspace method. Okay. So now I want to show you some numerics. So for a numerical demonstration, here we're looking at the estimation of ground and excited state energies of a transverse field Ising model as our same benchmark. So here we just pick some unit time step and try to do time evolution on a uniform time grid. And what we're plotting is the arrow in the energy estimation versus the number of time steps we take. The left figure shows the result using a multi-observable signal, whereas the right figure shows a single observable result. So here we see the MODMD, the multi-observable version, really converges pretty rapidly across all the low-lying energies, especially for excited state where the single observable version tends to stagnate. But here I want to say that although the excited state energy convergence looks worse here, but then the ground state convergence we showed in previous work is really comparable to some of the state-of-the-art methods, or even better in some cases. So the right figure is not really doing bad at all for the ground state. We can also look at the performance on chemical system, where we picked lithium hydride here as our molecular benchmark. Here we show the energy errors as a function of the number of time steps we take at a fixed bond length. In particular, we show it at the equilibrium bond length. But the results are similar for different bond length. Again, we see a rapid energy convergence in the multi-observable setting. So this can really lead to a pretty good improvement in accuracy with only a marginal cost. Okay, so I would just want to wrap up to say that here we've demonstrated that the time evolution can be combined with classical shadow to efficiently perform accurate energy calculations in many-body systems. And our ultimate goal is to explore the full potential of this framework, namely shadow plus DMD, where I think some of the problems beyond phase estimation will be interesting. So I'll end here, and then thank you all for listening.
So I have a quick one. So I got confused for you. You go back to the slide where you're doing the actual analysis with the metric that you had. So those are vectors. So you have a matrix of vectors, the order 3 tensor, and then you're doing the composition of that one. So you do simultaneous for all dimensions of the vectors, or each of them is a separate matrix?
So here we're literally stacking these vectors in rows, or in rows.
Oh, so you're setting it, it's still a 2D. It's not, it's not a 3D object.
It's still a 2D object.
Oh, okay. So those O's, I thought you're doing multiple observable that you care at the same time, or are those O's to help you just get the ground state?
So we can pick it depending on what we want. If we want some of the problems with these ground state method, it has to assume large overlap with that. It has to assume large overlap between the initial state and the ground state. But then these O's can really excite you to the excited state manifold. So we can start with a simple initial state and then do multiple O's to probe different eigenspaces.
And can I reverse this and use those O's as actual observable? So for instance, I get the energy and I also get the 2-point correlation factor for a method, or not really? Can I?
So for doing 2-point correlation functions, not we can still use this framework, but the circuit is not exactly the same. So you have to rerun.
How do you choose these operators O1 to OIs? Maybe you mentioned that before, but maybe I missed it.
Okay, so yeah, that's a very good question. So for these plots, what we chosen as O is just like random 2 local operators. So even we choose it randomly, for a spin model, we already see a great improvement. And there's systematic way for choosing these O's. For example, if you write the Hamiltonian in the Pauli basis, ideally you can pick the ones with a larger weight. So that if you look at replace this O by H here, what it really does is try to amplify the amplitude in the extremal eigenvalues. Powers of H or something like that, and we really try to boost up the amplitude in the ground state versus those in the interior state.
Like a PCA kind of a thing done on the Hamiltonian and then applied on these O's would be better.
PCA.
Some kind of a
Yeah, something like that.